All right, today we're going to discuss colligative properties. Colligative properties are properties that depend on the number of solute particles per solvent particles, not on the chemical nature. So things that we're going to be investigating are changes in vapor pressure, changes in boiling point, changes in freezing point, and changes in osmotic pressure. So dissolving a solute is going to affect these properties of a solution. All right, we'll start with Raoult's law. We'll draw a picture of an equilibrium system. Let's say you have a liquid in a closed container. That liquid is going to evaporate, producing particles in the gaseous phase. Those particles in the gaseous phase are going to rejoin the liquid, and so we have an equilibrium system. So I'll just write it as substance X. It is going to evaporate. The liquid will evaporate to produce a gas, and then that gas can recondense. So it says the pressure of the vapor in the above equilibrium is known as the equilibrium vapor pressure. So remember, in order for a substance to vaporize, in order for a substance to evaporate, the particles that are changing from a liquid to a gas need to be at the surface, and they have to have enough kinetic energy to break free from their attractive forces and become individual particles in the gaseous phase. Now, when you have a solute dissolved in a solution, a couple things happen. So first of all, letter A says a non-volatile solute particles will be at the surface. So the proportion of solvent particles on the surface will be decreased. So not only will there be solvent particles on the surface, there will also be solute particles on the surface. There's a picture of this on page 515. If you take a look there, on the left we have just pure solvent. On the right you have a sugar solution. And so if there's a smaller proportion of solvent particles on the surface, that's going to affect the rates of evaporation and thus the equilibrium vapor pressure. Something else to keep in mind as well is that new interactions between solute and solvent particles must be considered. So you have attractions between the solute and solvent particles. Again, this is going to affect the ability of that liquid to evaporate. Now we'll talk later about ideal versus non-ideal solutions. For ideal solutions, they only consider A. Ideal solution, there are no attractive forces between solute and solvent. And so, nevertheless, no solution is truly ideal, but some do approach it pretty closely. Letter A says ideal solutions are where the attractive forces between solute and solvent particles are equal to the attractive forces that the solute and solvent particles have for themselves. So it's not that there's no attraction between the solute and solvent. Rather, the attraction between solute and solvent is the same as the attraction between solute and solutes and solvent particles. Because of this, then, the heat of solution, delta H, for the formation of these solutions is 0. Again, this is just for ideal situation. So what if you have a non-ionizing, non-volatile solute? Remember, a non-volatile solute is something that does not evaporate. So an example of that would be sugar, could be salt. Non-ionizing, though, that would be more like sugar than salt. Salt is an ionizing solute. We'll talk about electrolytes in our next lesson. So here's Raoult's law for non-ionizing, non-volatile solutes. So the vapor pressure of the solution is equal to the vapor pressure of the solvent by itself times, be careful, the mole fraction of the solvent. We've done mole fraction before, and I said you can calculate mole fraction for either solute or solvent. And the book does it different ways here. So if you use this formula, where you multiply the vapor pressure of the pure solvents by the mole fraction of the solvents, that will give you the vapor pressure of the resulting solution. The book goes through and does an example, as you'll see here in 14.4, where you calculate how much the vapor pressure is decreased by, and their setup is a little bit different. So let's take a look, 516. It says sucrose, a non-volatile, non-ionizing solute in water, determine the vapor pressure lowering. So how much does the vapor pressure go down by? At 25 degrees Celsius of the 1.25 mole sucrose solution in example 14.2, assume that the solution behaves ideally. The vapor pressure of pure water, we need to know that value, at 25 degrees Celsius is 23.8 torr. So using the values from example 14.2, you had 50 grams of sucrose and 117 grams of water. We want to find the mole fraction. Notice what they're doing here. They're doing the mole fraction of the solute. And so the mole fraction of sucrose is 0.0220. Multiply that by the vapor pressure of the water by itself. And this will give you how much the vapor pressure goes down by. So if you wanted to calculate the vapor pressure of the resulting solution, you would take the vapor pressure of the water by itself, 23.8 torr, minus 0.524 torr, and you'd get the vapor pressure of the solution. Or just use the mole fraction of the solvent. All right, let's go ahead and practice one. Number 37 on page 541. Go ahead and pause the video now. Here's the setup, kind of like the example. So I use the mole fraction of the sucrose. So how to find moles of sucrose first and moles of water. And got how much the vapor pressure goes down by. So remember, anytime you dissolve a non-volatile solute in a solvent, it's going to lower the vapor pressure. And so it decreases by 0.0631. Water by itself at 25 degrees Celsius has a vapor pressure of 23.76 torr. And so if it goes down by 0.0631, our resulting vapor pressure of the solution is 23.70 torr. Now I didn't do part C, but you would set that up kind of the same way, except that the vapor pressure of water by itself at 100 degrees Celsius, of course, is 760 torr. And so the vapor pressure, I believe, goes down by about 2 torr to 758. All right, what if you have a volatile solute? Remember, volatile means can easily or readily evaporate. So what if both the solvent and solute can evaporate? Well, both of them are going to then contribute to the vapor pressure of the solution. So we have a little different equation that we write for this. So I'm just going to write the PT, or this is again the vapor pressure of the solution. If you want to write that, that's fine. So we take the vapor pressure of component A. So we'll make a little key here. A is one of the gases, and B is the other gas, second gas. So vapor pressure of substance A by itself times its mole fraction times vapor pressure of the other substance times its mole fraction, add those up, and we get then the vapor pressure of the solution. Now if you go back to 516, take a look at figure 1410. We see the relationship between vapor pressure of the solute and vapor pressure of the solvent and how they affect then the vapor pressure of the solution. So of course, together, depending on how volatile they are, can affect the vapor pressure of the solution quite a bit. All right, 14.5 on the next page. Says at 40 degrees Celsius, the vapor pressure of pure heptane is 92.0 torr, and the vapor pressure of pure octane is 31 torr. Consider a solution that contains 1 mole of heptane and 4 moles of octane. Calculate the vapor pressure of each component and the total vapor pressure of the above solution. So again, just like we did before, we got to find the mole fraction of each component. So book shows finding heptane first, 0.200. We can subtract that from 1 as they're showing here. The mole fractions must add up to 1. They're kind of like a percent, if you recall. And then if you just take the mole fraction times the vapor pressure of that particular substance, you'll get the vapor pressure of that substance in the solution. So 18.4 torr for the heptane, 24.8 torr for the octane. And then if we apply this equation here, add up the vapor pressures of those two substances, then we get the total vapor pressure of that solution, in this case 43.2 torr. All right, let's try one out. Number 39 on page 541. Go ahead and pause the video. So here's our setup. We have equal amounts of those two substances. So our mole fraction is 0.5. And so multiply that by the vapor pressure of each substance by itself. Add those up. We get the total vapor pressure of 208 torr. All right, let's go to 517. Example 14.6. Says calculate the mole fractions of heptane and octane in the vapor that is in equilibrium with the solution in 14.5. So like we've seen before, if we go back to this equation, we can solve for mole fraction. So to find the mole fraction of a substance, we take the vapor pressure of the solution and divide it by the vapor pressure of that pure solvent. And so that's what's done in 14.6. Vapor pressure of heptane was 18.4 torr. Divide that by the vapor pressure of heptane in the solution is 18.4 torr. Vapor pressure of heptane by itself, 43.2 torr. Again, this is all coming from 14.5. 43.2 is the total vapor pressure of that solution. Divide those and you get 0.426. That's the mole fraction of heptane. You can subtract that from 1 to find the mole fraction of octane, or do the same thing with octane, where you take the vapor pressure of the octane divided by the total pressure, and you get the mole fraction of that substance. All right, try that out for number 41. You're looking for the mole fraction of each component. Go ahead and pause now. So here's the setup. You get 0.947 mole fraction for the ethane. This is for ethane. And then the propane would be 0.053.